Hello and welcome to the Calm Science channel. Tonight our attention drifts upward toward the highest reaches of our planet, toward places where the air thins, sound softens, and the night sky feels unusually near. Mountains rise from the earth like slow frozen motions, shaped by forces that began long before human memory. They are expressions of a restless planet, lifted by pressure, sculpted by cold, and softened by time. Snow settles on their peaks, sometimes remaining for longer than any civilization below has existed. To observe a mountain is to quietly witness the passage of deep time. They appear still, yet they are never truly at rest, changing through steady cycles of wear and renewal. Tonight, we will move gently through this quiet immensity. You will explore how mountains come into being, how they influence air and water, and how they quietly shape the lives that exist along their slopes. If these slow explorations bring you calm, you're welcome to like, subscribe, or leave a thought beneath the video. It helps others discover this peaceful space, one resting mind at a time. For now, there is nothing to do but breathe. Let your shoulders soften. Allow your thoughts to slow as mountains take form in your imagination. When you're ready, we'll begin. Mountains begin their lives far below the surface, where enormous sections of Earth's crust move so slowly they seem motionless. Continents drift at a pace similar to growing fingernails. Yet when these vast plates meet, their combined force reshapes the planet. Over immense spans of time, rock layers compress, bend, and fold. What once lay beneath ancient seas gradually rises to become ridges, slopes, and towering summits. This process unfolds patiently, driven by heat and movement deep within the mantle. The Himalayas emerged through such a meeting. When the Indian landmass, prestigious stone, was pushed skyward, forming the tallest mountain range on Earth. Each peak holds a record of that collision, a permanent impression of pressure turned solid to lead. Upon a mountain is to see the aftermath of continents meeting and refusing to yield, transforming invisible motion into lasting flare. In some regions, mountains grow faster than they can be worn away. Erosion is constant, shaping rock through rain, wind, and ice. But where tectonic forces remain strong, the land can rise more quickly than it is broken down. In these places, summits continue to climb. Even as they slowly crumble, parts of the Andes, for example, still rise by several millimeters each year. The crest beneath them thickens gradually, as if lifting itself upward. Rivers carve into the rock. But when uplift outpaces erosion, they become confined to steep. Narrow channels, valleys deepen, cliffs sharpen, and the landscape becomes dramatic and tense. This balance between construction and decay gives mountains their character, turning time into a quiet contest between forces that build and those that wear away. Every rising range represents a slow triumph of Earth's interior over the patient work of the atmosphere above. Entire mountain systems also travel across the planet. Though they appear fixed, mountains ride atop moving continents as tectonic plates drift. They carry entire ranges with them. The rocks of the Appalachian Mountains once formed closer to the equator, and have since journeyed thousands of kilometers north. The Alps, too, have shifted position as the crust beneath them slowly rearranged. Even volcanic peaks, which seem firmly anchored, move if the deep heat sources below them change over time. Within many mountains, scientists find traces of earlier worlds. Marine fossils embedded in stone now find high above sea level. These clues reveal long journeys through changing climates and latitudes. Though imperceptible within a human lifetime, continental motion never truly pauses. Across deep time, mountains drift silently, with the land beneath them. The Himalayas continue to rise even now. When India collided with Asia roughly 50 million years ago, the movement did not simply end. The pressure persists, pushing the Tibetan plateau higher and folding the crust into immense ridges. Each year, the range gains a small amount of height, roughly the thickness of a fingernail. This ongoing movement releases its energy to earthquakes, reminding the region that the collision remains active. As the land lists, glaciers shape the peaks, feeding rivers that support countless lives far below mountains. Like Everest and K2, are not static monuments from the distant past. They are dynamic, shifting forms, growing, shedding, and reshaping themselves continuously. Every small rise is a quiet signal from the planet's interior, a reminder that the mountains we see today are still in the process of becoming. Long before the Andes rose above South America, their stones rested beneath an ancient sea. What is now towering rock once existed as layers of sand, shells, and corals settling quietly on the ocean floor. Over immense spans of time, these sediments hardened into limestone, shale, and sandstone. When the Nazca Plate began sliding beneath the continent, those ocean layers were compressed, bent, and lifted upward. The seafloor slowly transformed into sharp ridges and sweeping peaks. Even today, traces of that watery past remain. Fossilized shells can be found high in the mountains, gentle evidence that these heights were once submerged. Volcanoes also emerged along the growing range, spreading lava across the rising land and adding new stone to the structure. Deep beneath the surface, earthquakes still ripple where the old ocean crust continues its descent. To stand atop an Andean summit is to rest upon the remains of a vanished sea, raised patiently into the sky. The Appalachian Mountains tell a very different story. Today they appear as soft, forested hills stretching across the eastern United States. Yet long ago, they stood among the tallest ranges on Earth. More than 400 million years in the past, ancient continents collided and folded the crust into towering peaks, comparable in height to today's Himalayas. Time slowly changed them. Rain, wind, and ice wore away the sharp edges, carrying stone grain by grain toward the sea. What remains now are the deep roots of that former range, exposed and smoothed by age. Beneath the trees lie rocks that were once heated, twisted, and compressed under enormous pressure. The rounded ridgelines resemble the worn remains of something once immense. Though quiet in appearance, the Appalachians still carry the memory of Earth's restless movements, a lasting reminder that mountains rise and fade in cycles far longer than human history. Compared to many ranges, the Alps are relatively young. Though they feel ancient to us, they formed only about 40 million years ago when the African landmass pressed northward into Europe. This youth gives them their dramatic character. Sharp ridges, steep faces, and bright snowfields reflect the landscape still in the early stages of its transformation. Glaciers continue to shape the Alps, carving valleys and sharpening summits because uplift has not yet ceased. Avalanches and landslides remain common, signs of a range still adjusting to gravity and erosion. Within in their stone layers are fossils of marine life, wide traces of the Tethys Ocean that once covered this region. The Alps exist in a delicate moment between emergence and decay, high enough to influence weather, yet young enough to remember the sea. The Rocky Mountains formed in an unexpected place, unlike many ranges that rise along the edges of tectonic plates. The Rockies emerged far inland around 70 million years ago. An oceanic plate slid beneath North America at an unusually shallow angles. Instead of sinking deep, it transmitted pressure far across the continent. That force buckled across hundreds of miles from the coastline, lifting peaks where flat land had once stretched. Over time, rivers carved through the elevated rock, revealing layers of ancient seabed and volcanic material. These exposed strata continue to help scientists understand how distant forces can misshape entire regions. The Rockies stand as proof that Earth's movements do not always follow simple patterns. Their story shows how subtle changes deep below the surface can quietly redefine landscapes far from the edges of the world. Antarctica holds mountains hidden beneath its ice. Beneath miles of frozen surface lies an unseen range known as the Kamberdzev Mountain. Discovered through radar and gravity measurements, these peaks rival the height of the Alps and stretch hundreds of miles across the continent's interior. No human has ever seen them directly. They remain buried under ice that has endured for more than 30 million years. Their origins are still uncertain, though evidence suggests they may have formed through ancient continental collisions. Long before Antarctica became frozen, these hidden mountains shaped the flow of ice above them, guiding glaciers and enclosing dark, subglacial lakes. Even on the coldest continent, entire mountain worlds lie sleeping, untouched by sky or sun for tens of millions of years. And beyond the continents, there are mountains hidden beneath the oceans, some rising even higher than Everest. Far beneath the ocean's surface, beyond the reach of sunlight, exists a mountain system larger than any found on land. Along the mid-ocean ridge, molten rock slowly rises from deep within the mantle, cooling as it meets seawater and building immense underwater peaks. Measured from their hidden bases to their highest points, some of these mountains surpass Mount Everest in total height. This vast chain stretches around the planet for more than 40,000 miles, tracing a continuous path through the world's oceans. Along its slopes, volcanic vents release heat and minerals into the dark water, supporting unusual ecosystems that thrive without light. Steep cliffs, ridges, and valleys form an unseen landscape, more extensive than any mountain range above the waves. When scientists first mapped it using sonar, they discovered that Earth's greatest mountain system had been concealed beneath the sea all along. It is a realm shaped by fire and water, constantly active, quietly reshaping the planet from below. This underwater network is the largest mountain range on Earth. The mid-ocean ridge forms a continuous volcanic spine that wraps around the globe like a seam holding the crust together. Hidden under miles of ocean, it marks where tectonic plates slowly drift apart, allowing new crust to form as molten rock cools and hardens. The ridge winds through every major ocean, crossing vast basins and even extending beneath polar ice. Despite its invisibility, it covers nearly a quarter of the planet's surface. Along its crest, superheated water erupts from deep fissures, rich with minerals that sustain life in complete darkness. Creatures gather around these vents, drawing energy from chemical reactions instead of sunlight. The ridge is not a single mountain, but an entire living system, continuously renewing the ocean floor. It It is a steady pulse of Earth's surface, endlessly creating new ground beneath the waves. Some mountains lie hidden beneath ice rather than water. In Antarctica and Greenland, thick ice sheets conceal rugged terrain that has not been exposed for millions of years. Radar surveys reveal buried ranges, deep valleys, and broad plateaus shaped long before ice claimed the land. These landscapes were carved like rivers and ancient glaciers that disappeared as the climate changed. The immense weight of the ice presses downward, bending the crust and forming deep basins where dark subglacial lakes persist beneath Antarctica. Scientists have traced entire hidden drainage systems flowing around unseen peaks. The ice preserves these features like a frozen archive, capturing a version of the planet long gone. If the ice were ever removed, continents would appear transformed, revealing mountains older than human memory, kept in silence beneath an immense white cover of time. Not all mountains take millions of years to form. Volcanoes can rise within a human lifetime. The magma finds a path to the surface. It builds layer upon layer of ash and lava, slowly solidifying into new land. In some cases, this process unfolds with astonishing speed. In the mid-20th century, a volcano emerged suddenly from a farmer's field in Mexico. Within days, smoke darkened the sky. Within a year, a cone more than 1,000 feet high had formed. Over the next several years, the volcano continued to grow, eventually standing taller than many city skyscrapers. Nearby villages were buried in ash, while the surrounding landscape became a living record of mountain formation. Watching the volcano rise is witnessing Earth at work in real time, a reminder that the forces shaping the planet were not always distant or quiet. Some volcanoes do not grow tall and steep, but wide and expansive, known as shield volcanoes. They spread outward through flowing lava that travels great distances before cooling. Their gentle slopes resemble a shield resting on the ground. In places like Hawaii and Iceland, these volcanoes show that mountains are not always born in violence. Some rise slowly and steadily, shaped by patient rivers of fire beneath a quiet sky. Beyond Earth, mountains reach even greater extremes. On Mars stands a volcano, so immense that it dwarfs every mountain on our planet. Its slopes extend for hundreds of miles, and its summit rises more than twice the height of Everest. Its towering structure reminds us that mountain building is not unique to Earth, but a universal process, shaping worlds across the solar system. Light hangs dividing to the season. No total was men so confused and seas of volcanoes, so immense that it dwarfs every mountain on our planet. Its slopes extend for hundreds of miles, and its summit rises more than twice the height of Everest. This tower The mountain on Mars is so immense that its slope subtly follows the curve of the planet itself. Scientists believe it reached such extraordinary size because Mars does not have shifting tectonic plates. The ground beneath the volcano never moved away. Each eruption occurred in the same location, allowing lava to accumulate layer by layer over millions of years. Slowly, the mountain spread outward and upward, growing broader rather than sharply steep. The result is a vast, gently sloping giant with cliff faces far taller than any found on Earth. Seen from orbit, it overwhelms the surrounding terrain, dominating the Martian surface like a silent landmark frozen in time. Olympus Mons stands as evidence that mountain building follows universal rules, shaped not by Earth alone, but by forces that operate across planets and space itself. Some mountains are built not from molten rock or crushed continents, but from living organisms in warm, shallow seas. Coral reefs slowly grow as countless tiny creatures build calcium skeletons over long ages. These reefs can become massive limestone structures when tectonic forces later lift them above sea level. They form entire mountain ranges. In places like New Guinea, towering peaks are composed largely of ancient coral, fossilized shells, and marine life are embedded high within cliffs far above the present ocean. These mountains preserve the memory of seas that once covered the land. Rain and flowing water slowly dissolve the limestone, carving caves, sinkholes, and sharp spires. The result is karst terrain, landscape shaped by water and time. And these mountains, every grain of stone was once alive, assembled patiently by countless small creatures and peaks that now rise toward the sky. Beyond Earth, the mountains are made almost entirely of ice. In the distant outer solar system, frozen worlds host peaks as solid as stone. On Jupiter's moon, Europa, and Saturn's moon, Enceladus, the surface consists of thick ice covering global oceans. Tectonic forces fracture and shift this frozen crust. Enormous blocks of ice collide, tilt and sack, forming ridges and mountains thousands of feet tall. On Pluto, substances like nitrogen and methane freeze into materials strong enough to behave like rock glaciers. Of these exotic ices flow slowly across the surface, building bright, fractured peaks that gleam faintly in distant Samadini. Some of these icy mountains, liquid water may still exist, warmed by internal heat. If so, hidden oceans could provide environments suitable for life. These frozen ranges remind us that mountain formation is not limited to rock, but follows physical laws that shape even the coldest worlds. Some mountains rise directly from active lava fields. In places like Iceland and Hawaii, small peaks emerge amid broad plains of cooling basalt. These are cinder cones, formed when eruptions hurl fragments of molten rock into the air. As the fragments fall back to the ground, they cool and accumulate into steep, conical hills. Some cinder cones reach only a few hundred feet in height, while others climb much higher. Their slopes like dark ash and glowing red stone. In regions such as Iceland's Haldoran Field, new cones can appear within years. The air carries the sharp scent of sulfur, and the ground vibrates faintly with hidden heat, though modest in size compared to great mountain ranges. These peaks are remarkable for their youth. They stand as fresh evidence the Earth continues to shape new summits within human view. A mountain's color reveals its history. Every hue across a mountainside reflects the minerals and processes that formed it. Red tones often indicate iron-rich rock altered by oxygen. Green shades may signal copper-bearing minerals. Pale limestone cliffs point to ancient ocean floors, while dark volcanic stone records eruptions from deep within the planet. In arid regions, layered sediments paint mountains in shades of pink, gold, and violet. Light transforms these colors throughout the day, of peaks glowing warmly at sunrise and cooling into blues and grays at dusk. Even snow can carry stories, tinted by volcanic ash or desert dust, carried on distant winds to geologists. These colors fall in the language of chemistry and time. To the resting observer, they are Earth's memory expressed through beauty. These ancient stones have endured collisions, erosion, and the rise and fall of entire continents. They are remnants of Earth's earliest crust, altered by immense pressure yet never fully destroyed. To hold such a rock is to touch material from a time when the planet's surface was still cooling and life had not yet emerged. Mountains formed from these stones are like geological fossils, preserving within their crystals the story of Earth's beginnings. They are witnesses to an age older than oceans, older than continents, older than memory itself. The oldest mountain range on Earth no longer looks like a mountain at all. In South Africa, the Barberton Greenstone Belt contains traces of some of the planet's first mountains, formed more than 3 billion years ago. Time has worn them down into low hills and twisted rock formations. What remains are fragments of ancient volcanic peaks and deep ocean floors, reshaped again and again by erosion and shifting crust. Within these rocks lie microscopic fossils of some of Earth's earliest life, simple bacteria preserved as faint impressions in stone. These mountains existed under skies filled with volcanic haze, when the oceans carried dissolved iron and oxygen was scarce. They witnessed the slow transformation of the planet, from lifeless stone to a world that could breathe. Though their heights have long since faded, their story remains written into every grain. The Barberton Range is a quiet memory of Earth before forests, before animals, before familiar skies. A whisper from a world still learning how to live. Mountain peaks can shape the weather around them. When moist air is pushed upward along a slope, it cools as it rises, allowing clouds to form near the summit. As that air passes over the ridge and descends, it warms again, often leaving dry conditions behind. This process creates rain shadows and defines entire climates. The Andes help maintain the dryness of the Atacama Desert, while the Himalayas shield vast regions from cold northern winds. Even a single peak can influence its surroundings. Rising air can trigger localized storms, with clouds gathering around a summit like a temporary crown. Mountains guide rainfall, redirect winds, and determine where fog settles. In this way, they are not merely shaped by the atmosphere, they actively shape it, breathing structure into the sky above them. Clouds often form and dissolve along mountain slopes. On a breezy day, you might watch mist appear suddenly against the rock, only to fade moments later. As air moves upward, it cools just enough for moisture to condense. A short distance higher, the air may dry again, and the cloud disappears. These fleeting formations are called orographic clouds, created directly by the mountain's presence. In some places they linger in soft bands, draping the peak like fabric tigers. They bring unexpected fog or brief showers. From afar they make the mountains seem animated, as though it were gently inhaling and exhaling mist. Each cloud is temporary, born from a quiet balance of wind, temperature, and shape. Some mountain fills clouds that seem to stand still. When the steady winds, smooth lens-shaped clouds can form above peaks and remain suspended in place. These lenticular clouds develop when air flows over a mountain, then repeating waves, rising, cooling and sinking again. Their curved outlines often glow softly at sunrise or sunset, painted in pinks and golds. Though they appear motionless, the air within them moves rapidly. Pilots avoid flying near them due to the turbulence below. In regions near peaks like Mount Fuji or Mount Rainier, these clouds sometimes stack in layers, hovering like floating discs. For centuries they inspired myths and misinterpretations in truth. They are simply the movement of air made visible, revealing hidden waves in the atmosphere. At sunrise, mountain shadows can stretch across vast distances. When the sun is low on the horizon, a tall peak casts a long, triangular shadow that can extend for hundreds of miles. Even irregular mountains pretty sharp, pyramid-shaped silhouettes due to the geometry of light at dawn. On towering peaks, climbers sometimes watch their own mountain projected across the glowing sky. As the sun climbs higher, the shadow slowly shortens and dissolves into brightness. The moment lasts only minutes, and it feels unhurried. It is as if the mountain is greeting the day, releasing that final breath of darkness before the light fully arrives. On certain mountains, you may glimpse your own rainbow in drifting mist. When sunlight shines from behind you and meets a veil of cloud or fog below, a circle of color can appear around your shadow. This phenomenon is known as a glory, a delicate ring created as light scatters through countless tiny droplets, suspended in the air. From aircraft, it can surround the plain silhouette, but on a mountain, it feels intimate. The halo follows your movement, appearing and fading as the mist shifts. Climbers at high elevations often describe the experience with awe, referring to it as the broken specter. Sometimes the shadow looks enormous, stretched by distance and perspective, as if the mountain itself were reflecting your presence in light. In that moment, physics feels poetic. Light, air, and perception merge, and the boundary between observer and landscape softens into color. High mountain air holds less oxygen, yet it carries more cosmic radiation. As elevation increases, the protective layer of atmosphere above grows thinner. Each breath contains fewer oxygen molecules, requiring the body to adapt at the same time. The reduced shielding allows more cosmic rays from space to reach the surface. At extreme heights, such as the summit of Everest, radiation exposure can be roughly twice that experienced at sea level. Over time, this invisible energy affects both people and equipment. Pilots and mountaineers accumulate higher exposure simply by spending hours above the clouds. In return for this harshness, the air offers remarkable clarity. Stars appear sharper, and the sky deepens into a darker, richer blue than most ever witnessed. Mountains lift us closer, not only to the view of the heavens, but to the quiet energies that flow through space itself. Mountains also shape wind patterns on a planetary scale. When moving air encounters a range, it is forced upward, cooling and shedding moisture. As it descends on the opposite side, it warms and dries, creating pressure differences that ripple outward. These shifts can link together, influencing weather far beyond the mountains themselves. The Himalayas help drive the Asian monsoon, while the Andes guide jet streams across South America. Even smaller ranges can redirect storms and influence trade winds high above. Waves of air generated by mountains travel through the atmosphere, their energy detectable from orbit. Each range plays a subtle role in Earth's circulation, like a note in a vast, ongoing composition. Though the peaks stand still, they quietly conduct the movement of the sky. Mountain air carries traces of distant lands. Winds sweeping across peaks are filled with microscopic particles lifted from faraway deserts, oceans, and forests. Dust from the Sahara can cross continents and oceans before settling on alpine snow. These tiny grains carry minerals, pollen, and sometimes microorganisms. When they darken snowfields, they allow sunlight to be absorbed more easily, accelerating melt volcanic ash, sea salt, and smoke from distant fires join us in this journey through the atmosphere. Scientists study layers of mountain snow as records of past climates, reading patterns of drought, storms, and shifting winds. Even the highest, most isolated summits breathe air that has traveled the entire planet. Every gust is part of a shared atmospheric story. Snowflakes form differently at high elevations in the cold. Thin air above mountain slopes, ice crystals grow under unique conditions. Temperature, humidity, and freezing speed shape each flake structure at higher altitudes. The air is often drier and colder, favoring slender needles, columns and hollow shapes rather than wide, branching stars. Some crystals form as clean hexagonal plates that catch the light like grass. As snowflakes fall through layers of air, they continue to change, adding ridges and facets along the way. No two follow the same journey. The snow that gathers on mountain slopes is built from countless individual designs, each one a quiet record of the atmosphere that formed it. Every crystal is a small story of air and cold, drifting gently back to the earth. Some mountain glaciers move faster than a person can walk. Glaciers often appear motionless, yet many are quietly in motion. Deep within their frozen mass, tremendous pressure causes ice to behave not as a solid, but as a slow-flowing substance in places like Greenland and Alaska. Certain glaciers advance several feet each day. Some have even been measured traveling miles within a single year, outpacing a leisurely walk across the land below. This movement is made possible by meltwater beneath the ice, which acts as a slick layer, allowing the glacier to slide over bedrock as it travels. The ice grinds rock into fine powder and carves deep channels through the mountains. If you stand nearby, you may hear the glacier crack, groan, and sigh as fractures shift and reseal, almost like a slow breath. Though it looks frozen and still, a glacier is a river paused in time, always moving, always reshaping the mountains it drapes across, carrying fragments of their story toward the sea. Other glaciers are so cold that they have not moved for thousands of years. In the most extreme environments, ice becomes rigid and brittle, locked firmly in place. These stagnant glaciers are found in parts of Antarctica and at very high elevations in the Himalayas. Layer upon layer of snow has compressed into dense ice, trapping tiny bubbles of ancient air within. Scientists drill long cores from this ice, extracting records of the atmosphere stretching back hundreds of thousands of years. Each compressed layer marks a season, a storm, or a distant volcanic eruption. These frozen archives preserve evidence of shifting climates and environmental changes that influence civilizations far away. Though these glaciers appear lifeless, they quietly hold the breath of ancient Earth, sealed away in perfect stillness. Each trapped bubble is a whisper from a vanished world, waiting patiently to be heard. Glaciers shape valleys that endure long after civilizations fade. As ice advances and retreats, it sculpts mountains into wide, U-shaped valleys, smoothing cliffs and deepening basins over vast spans of time. The slow pressure of moving ice polishes stone and leaves behind landforms that persist for tens of thousands of years. When glaciers melt away, their work remains rivers. Follow the paths they carved, lakes, fill the hollows they left behind. Some of the world's most dramatic valleys, including those in Norway and New Zealand, owe their shape to ice that vanished long before written history. Even where glaciers no longer exist, their presence is etched into every curve of the land. They are architects of deep time, working not in years, but in ages, shaping landscapes with quiet precision. Some mountains serve as windows into Earth's ancient climates. The layers of rock within the mountains are more than stacked stone. They are records of past worlds. Each layer captures conditions from a different era, preserved through minerals, textures, and fossils. By analyzing chemical signatures in limestone or the fine grains of volcanic ash, scientists can reconstruct ancient temperatures, rainfall, and ocean chemistry. Some Himalayan peaks contain shells from a time when the region lay beneath the sea. Other mountains hold desert sands now, lifted high above the plains. Climbing a mountain can feel like traveling backwards through time, moving from the present into distant ages. Heavy exposed layers that preserve memory of heat, water, and life that once shaped the planet. Mountains store much of the world's fresh water as snow and ice high above the valleys. Snow accumulates year after year, slowly compressing into glaciers that hold the majority of Earth's accessible fresh water. These frozen reserves feed rivers that support billions of people across continents. The seasons change, melting snow and ice release water gradually into streams, lakes, reservoirs. When this rhythm is disrupted, when snow arrives too late or melts too quickly, drought can follow ranges like the Himalayas, Andes, and Rockies, often called the planet's water towers. Because so many lives depend on their steady cycle of freezing and thawing, each winter leads to a watering crystalline flow. Each warmer season, they return it gently to the world below. To watch snow settle on a high keep is to witness Earth quietly saving life, one delicate crystal at a time. At high elevation, even boiling water becomes a quiet lesson in physics. The simple act of heating a pot reveals how altitude reshapes the rules of air and heat. As pressure drops, water transforms more easily into vapor, reminding us that mountains change not only the body, but the behavior of the world itself. When a person climbs to high altitude, the body responds almost immediately. With less oxygen available, sensors in the kidneys detect the change and release a hormone that signals the bone marrow to produce additional red blood cells. Within days, these cells increase in number, improving the blood's ability to gather oxygen from thin air. Over weeks, the blood grows slightly thicker, carrying each breath more efficiently through the body. This adaptation allows people to function where oxygen levels are dramatically lower than at sea level. Athletes often train at elevation for this reason, returning with improved endurance once they descend. It is a quiet collaboration between biology and physics, a reminder that life can reshape itself to meet the mountain's demands. Each heartbeat at altitude reflects this adjustment, the body steadily rewriting its chemistry in response to the air around it. The highest permanent settlement on Earth sits above the level of many clouds. High in the Peruvian Andes lies La Rinconada, a mining town perched more than 16,000 feet above sea level. Here, clouds drift beneath the streets and newcomers struggle for breath within minutes of arrival. Yet tens of thousands of people live and work in this thin air, extracting gold where water boils at low temperatures. And every movement requires effort. The town lacks many basic comforts and daily life is physically exhausting. Still, its residents endure, adapted to conditions that would overwhelm most visitors. Above them lie glaciers and snowfields below. The rest of the world feels distant and unreal. Days are bright with intense sunlight. Nights bitterly cold in this fragile place. Life persists at the edge of human possibility, showing how adaptable home can be. Human communities have lived among mountains for thousands of years. Long before exploration and recreation, people settled high valleys and mountain passes. In the Andes, Quechua and Aymara, farmers developed terrace agriculture, cultivating crops like potatoes and quinoa in thin air. In the Himalayas, Sherpa villages formed along ancient trade routes, thriving among clouds and snow. Across the world, mountain cultures emerged in places like the Atlas Mountains, the Caucasus, and the highlands of Asia. Language, music, and architecture grew in harmony with steep slopes and isolation. Life at altitude demanded resilience and fostered deep spiritual ties to the land for many cultures. Mountains were not barriers, but living beings, guides, guardians, and teachers. To walk among these communities is to see that humans have long belonged in the mountains, not as conquerors, but as respectful companions. Throughout history, people have built sacred places on high ground to feel closer to the sky. Ancient civilizations often raised temples and shrines on peaks and ridges, believing height brought them nearer to the divine and grace. Mount Olympus was revered as the dwelling place of gods. In the Andes, the Inca placed offerings on volcanic summits rising far above the clouds. In Japan, climbing Mount Fuji became both a physical and spiritual journey. Across continents, hilltop sanctuaries follow the same instinct. Elevation symbolized transcendence, a thinning of the boundary between earth and heaven building. And such places required devotion and resolve. Each stone laid high above the plains carried a shared human longing. To rise, to reach, to connect with something greater than the ground beneath our feet. Pilgrims once crossed glaciers to reach holy destinations. Long before modern travel, faith led people through snowfields and over frozen passes. In Tibet, devotees journeyed for months across icy terrain to reach remote monasteries. In the Alps, travelers crossed glaciers to arrive at shelters like the Great St. Bernard Hospice, where refuge awaited in the thin air. These journeys were acts of endurance as much as belief. Pilgrims carried little, depending on trust, community, and perseverance. Every step was part of the devotion. Even today, hikers follow these ancient paths, unknowingly matching the footsteps of generations past. In the silence of high places surrounded by stone, humanity's search for meaning has always climbed upward, guided by light and quiet determination. Across nearly every culture, mountains have been imagined as sacred homes of higher powers. Their height, their silence, and their tendency to disappear into cloud made them feel set apart from ordinary land. To early observers, peaks were not just stone, but places where the sky seemed close enough to listen. In Greek tradition, Zeus ruled from storm-wrapped Mount Olympus. In Hindu belief, Mount Kailash stands as the center of the universe, the dwelling of Shiva. In Japan, Mount Fuji is home to the goddess Senjin. In Polynesian stories, volcanoes are living ancestors, beings that travel, argue, and remember. When lightning struck a summit, it was not seen as weather, but as communication. Even today, certain mountains remain unclimbed out of respect for spiritual tradition. Whether viewed as guardians, gods, or sleeping spirits, mountains continue to serve as bridges between the human world and something greater. Places where the earth itself seems to reach upward in quiet devotion. Many ancient societies believe mountains form the central pillar of existence. The idea of a world mountain appears repeatedly in myth. The Greeks named Olympus, Hindu cosmology described Mount Meru, Norse tradition imagined Yggdrasil, the great tree connecting the heavens, the living world, and the depths below in Mesoamerica. Step pyramids were built to echo sacred peaks, mirroring the same connection between realms. These ideas endured because mountains embody balance and permanence. Standing on a summit and gazing outward in all directions can feel like occupying a still point at the center of motion, where the sky appears to rotate around the land. Such beliefs were not simply superstition, but intuitive attempts to understand order, stability, and humanity's place within the cosmos. Mountains felt like the spine of the world, holding it upright against chaos. Even today, we instinctively turn to high places for perspective, sensing that they offer both grounding and orientation. Some mountains were believed to touch the heavens themselves. The four flighter satellites imagined peaks that reached into divine territory. In Mesopotamian legend, Mount Mashu guarded the path of the rising sun. In biblical tradition, Moses climbed Mount Sinai to receive law amid thunder and cloud. The Inca believed their highest peaks guided souls toward the afterlife. These stories gave mountains a sacred geography. Height became a symbol of transcendence. To climb upward was not merely to rise in space, but to move closer to the divine thin air. Deep silence and the brilliance of stars reinforced the feeling of standing at a boundary between worlds. Even now, reaching a high summit can awaken the same quiet sense of infinity that once shaped myth. Mountains are struck by lightning, more frequently than any other landforms. Rising into storm paths, peaks act as natural conductors for electrical charge. As energy builds within clouds, summits concentrate the imbalance until lightning discharges violently into stone. Tall peaks can be struck hundreds of times each year. On mountains like Rainier or the Matterhorn, climbers sometimes experience static buildup. Before a strike, chairlifts, metal tools vibrate in the air against a buzz. In those moments, trees may splinter and rock and shatter. Sometimes lightning melts sand or stone into twisting glass called fulgurates. Each strike is a reminder that even the hardest rock yields to the sky's energy. In the distance, the flashes are beautiful. Weave connections between earth and atmosphere, lighting the highest places like glowing crowns. Some peaks seem to hum with electricity during storms before lightning breaks. The air around the summit can fill with static charge. The faint sound may ripple through the air, and objects begin to glow softly. Climbers have described hearing an eerie, almost musical hum as the ions gather along the ridge. At times, pale blue light flickers at the tips of metal tools or around raised hands. This phenomenon, known as seep down those fires, signals extreme electrical tension. It is mesmerizing and dangerous, often preceding a lightning strike where moments met instant. The mountain feels alive, vibrating with invisible energy, like a vast instrument briefly played by the sky itself. Deep within mountains, certain minerals quietly encode invisible forces. Some rocks contain iron and nickel-rich grains that respond to Earth's magnetic field as they form. When molten material cools far below the surface, these minerals align themselves with the magnetic direction of that moment. Once locked into solid rock, that alignment can remain unchanged for millions of years. Large concentrations of minerals such as magnetite can create subtle magnetic irregularities in mountain regions. Instruments can detect these faint disturbances, and in rare places, compasses may drift or behave unpredictably. To scientists, these anomalies are invaluable. They reveal how continents have shifted and how Earth's magnetic field has wandered over vast stretches of time. Mountains become magnetic archives, holding delicate records of forces we cannot see. Each tiny mineral grain acts as a frozen compass, pointing not to today's north, but to where north once existed long ago. Some mountain rocks preserve the movement of Earth's magnetic poles themselves. As molten rock cools and hardens, the magnetic minerals inside it align with the planet's magnetic field at that instant. Once the rock solidifies, this orientation is fixed by examining rocks of different ages. Scientists can trace how the magnetic poles have shifted, flipped, and drifted across the globe. This field of study, called pyromagnetism, has revealed that continents have traveled thousands of miles and rotated in surprising ways. In some ancient mountain ranges, rock layers show the directions we now call north once pointed elsewhere. Entirely beneath our feet lie quiet maps of planetary motion. By preserving these alignments, mountains become libraries of direction, storing the memory of a planet that is always turning, even when the compass itself cannot tell the whole story. Earthquakes can reshape mountains in moments. While most peaks rise slowly, sudden shifts deep underground can transform them in seconds. When stress builds along faults and is abruptly released, rock can be pressed upward or collapse without warning. In 1960, a massive earthquake in Chile lifted sections of coastline by more than 10 feet, forming new cliffs almost instantly. Elsewhere, violent shaking can trigger landslides that erase slopes that stood for thousands of years in regions like the Himalayas and Alaska. Entire mountain faces have crumbled in moments. These events reveal the dual nature of Earth's forces. The same processes that build mountains can also dismantle them. The crust behaves like a living skin, cracking, mending, and reshaping itself through cycles of immense energy. Mountains rise from disorder, and sometimes with a single tremor they briefly return to it. Some lakes disappear when mountains shift during earthquakes or massive landslides. The ground beneath a lake can fracture or tilt, allowing water to drain away almost instantly. In China's Sichuan region, powerful earthquakes triggered landslides that both formed new mountain lakes and erased others within hours. In places like Iceland and Alaska, sudden ground movement has emptied glacial lakes in a single day. Leaving behind dry basins and stranded life, rivers can be dammed by fallen rock, only to burst later in destructive floods. These changes are dramatic reminders that mountains are not static. They breathe, shift, and transform, sometimes within a human lifetime. What feels permanent can vanish overnight, altered by motion deep within the planet's hidden structure. Landslides are among the fastest movements mountains can produce when rock and soil lose stability on steep slopes. Gravity accelerates them with astonishing speed. Some landslides race downhill at over 100 miles per hour, flattening forests and filling valleys in seconds. One of the most powerful recorded events in Alaska's Ladia Bay generated a wave more than 1,700 feet high. The energy released rivaled that of a major explosion, whether triggered by rain, melting snow, or earthquakes. Landslides offer little warning. Scientists study them to understand how heat and friction can briefly turn solid rock into flowing debris. Afterward, the land appears rewritten, as if a mountain has exhaled centuries of weight all at once. Avalanches can release energy comparable to powerful explosions, and layers of snow stack on steep slopes. Tension builds quite in between them. A small disturbance, a sound, a shift in temperature, a single fracture can cause the layers to collapse together, sending massive volumes of snow rushing downhill with unstoppable force. Avalanches can reach astonishing speeds, sometimes moving faster than 200 miles per hour. At their base, the pressure becomes immense, strong enough to snap mature trees and collapse solid structures. The force released in the large avalanche can rival that of small explosive blasts. And yet, within that violence exists a strange beauty, a flowing cascade of white rushing downward in near silence, until it reaches the valley below and fills the air with a shimmering mist of ice crystals. All winter long, mountains quietly store this energy. It remains hidden beneath layered snow, waiting for the brief moment when balance is lost. To those who study them, avalanches are both disaster and motion made visible. A powerful reminder that even snow, given the right conditions, can move with the force of thunder. Some avalanches generate powerful waves of air. As massive volumes of snow rush downhill, they shove the atmosphere ahead of them, creating an invisible blast that can race faster than the snow itself. This surge of air can reach hurricane strength, flattening trees, tearing roofs from buildings, and throwing debris far from the avalanche path. In the Alps and the Rockies, entire forests have been found snapped and flattened where no snow ever touched the ground. The destruction came not from ice, but from the moving wall of air ahead of it. In these moments, it is the breath of the avalanche that causes the damage, a sudden shock wave of displaced atmosphere. Afterward, the stillness feels unnatural. The land lies broken and silent, holding the echo of an unseen force that passed through in seconds. Snow itself can sometimes produce sound under rare conditions. Snowfields emit a low, haunting hum as layers shift and compress. The vibrating chain travels through tightly packed crystals, creating an invisible blast that can race faster than the snow itself. This surge of air can reach hurricane strength, flattening trees, tearing roofs from buildings, and throwing debris far from the avalanche path. In the Alps and the Rockies, entire forests have been found snapped and flattened when no snow ever touched the ground. The destruction came not from ice, but from the moving wall of air ahead of it. In these moments, it is the breath of the avalanche that causes the damage, a sudden shock wave of displaced atmosphere. Afterward, the stillness feels unnatural. The land lies broken and safe, holding the echo of an unseen force that passed through in seconds. Snow itself can sometimes produce sound under rare conditions. Snowfields emit a low, haunting hum as layers shift and compress. The vibration travels through tightly packed crystals, creating an invisible blast that can race faster than the snow itself. This surge of air can reach hurricane strength, flattening trees, tearing roofs from buildings, and throwing debris far from the avalanche path. In the Alps and the Rockies, entire forests have been found snapped and flattened where no snow ever touched the ground. The destruction came not from ice, but from the moving wall of air ahead of it. In these moments, it is the breath of the avalanche that causes the damage, a sudden shock wave of displaced atmosphere. Afterward, the stillness feels unnatural. The land lies broken and silent, holding the echo of an unseen force that passed through in seconds. In some regions, cave networks extend beneath entire mountain ranges. Beneath the Alps, the Dinaric Alps, and the Appalachians, vast systems of caverns connect. Through sinkholes, underground streams, and enormous chambers, large enough to feel cathedral-like. The Mammoth Cave system in Kentucky alone extends for hundreds of miles, with new passages still being discovered. These underground worlds formed over millions of years, as groundwater followed fractures in the rock, slowly expanding them into silent corridors. Many a home to unique life forms. Blind fish, pale insects, and delicate creatures adapted to eternal darkness. Above ground, people walk unaware that entire mountains rest upon hollow labyrinths carved by water, long before human history. Beneath many mountain ranges, underground rivers flow in complete silence. Rain and melting snow disappear into cracks in the rock, gathering into channels smoothed by time. These hidden rivers can travel great distances through stone, shaping landscapes no one sees. They move patiently through caverns older than the mountains themselves, continuing their quiet work far below the peaks above. Some underground ravines eventually return to the surface, bursting from cliff faces as cold springs. Others remain hidden forever, known only through faint echoes of dripping water deep within stone. Scientists trace these unseen flows by releasing harmless dyes and tracking their journey, sometimes watching bright color reappear miles away days or even weeks later. Far below the surface, water carries subtle messages from the world above, dissolving rock grain by grain. These rivers move slowly and steadily, patient as sleep itself, carving their paths through darkness. To imagine them is to picture the planet quietly inhaling its pulse, flowing gently beneath mountains of stone. Deep within mountain caverns, rare crystals grow in silence, far below the reach of sunlight. Still air and steady conditions allow minerals to form extraordinary structures. Droplets of water rich in dissolved minerals evaporate almost imperceptibly, leaving behind crystals of calcite, aragonite, and gypsum that expand like frozen blossoms. In Mexico's Cave of the Crystals, enormous selenite columns rise taller than buildings, glowing softly when light touches them. Some of these formations required hundreds of thousands of years to reach their size, growing at a pace measured in heartbeats rather than seasons. Their existence depends on perfect balance. Even small changes in temperature or humidity can halt their growth. Each crystal is a monument to patience, shaped by chemistry and time alone. In the deepest chambers of the earth, beauty continues to form unseen, resting quietly within the bones of the mountains. Many precious metals form range in mountains. Unstood gold, silver, and copper emerge from processes rooted deep in Earth's interior as magma cools slowly underground. It releases mineral-rich fluids that travel through cracks in the surrounding rock. When these fluids cool, they leave behind veins of metal locked within the stone. Over millions of years, erosion strips away the mountains above, eventually exposing these veins at the surface. Some of the world's richest metal deposits lie in regions where towering ranges once existed. Long erased by time, mining such places is, in a way, uncovering the remains of mountains that vanished before humans appeared. Each flip of gold or trace of silver carries a memory of fire, pressure, and deep geological transformation. Mountains are not only landmarks of stone, they are the furnaces in which Earth concentrates its hidden wealth. Diamonds reach the surface through the same forces that build mountains. Deep within the mantle, far below the crust, carbon atoms are compressed under immense pressure and heat until they crystallize into diamond. These gems remain buried for ages until powerful eruptions or tectonic collisions carry them upward. Volcanic channels known as kimmeronite pipes act as elevators from the deep earth, lifting diamonds closer to the surface during periods of intense geological activity. In regions such as Africa and Siberia, these processes left diamonds scattered through the roots of ancient mountain systems. Some diamonds contain microscopic inclusions, tiny fragments of minerals formed under extreme conditions that reveal details about Earth's interior, unreachable by any drill. Each gem is a message from profound depths, born in darkness and delivered through upheaval. The rocks of mountains also preserve the chemistry of Earth's earliest oceans. Long before complex life emerged, sediments on the seafloor recorded the composition of ancient seas. When those sediments were later lifted into mountain ranges, they carried their chemical signatures with them. By studying these rocks, scientists can reconstruct levels of oxygen, carbon, and iron in early oceans, tracing the slow changes that allowed life to arise. Some mountain limestones still show faint patterns left by stromatolites, layers built by ancient microbes billions of years ago. Others display bands of color that mark the planet's first encounter with oxygen. When iron began to rust in the sea, to hold such a storm as to catch the memory of Earth's earliest waters, preserved within rock and raised toward the sky. Mountains do not only reach upward, they carry the history of the oceans within them. Fossils found high in mountain ranges confirm that seas once covered the land far above any present shoreline. Shells, corals, and fish remains lie locked inside stone. These fossils are quiet witnesses to ancient oceans that once spread where peaks now stand. When tectonic forces collided and lifted the seafloor upward, these traces of marine life rose with it, sealed into limestone and shade. The Alps, the Himalayas, and the Rockies all contain such a maze, evidence that mountains were once submerged beneath shallow seas, millions of years ago. Each fossil is a reminder that Earth's surface is never fixed, and that even the highest places were once part of the ocean's floor. In the Alps, it is possible to experience 4 seasons within a single day. Morning sunlight can warm the slopes like spring, only to be replaced by summer storms, autumn winds, and sudden winter snow before nightfall. This constant change gives mountains a sense of presence, as though they are quietly breathing weather in and out. Standing on a summit beneath fast-moving clouds, you can watch nature transform itself, minute by minute, the sky rearranging its moods in real time. Some storms are born and vanish within a single valley in mountainous terrain. Air behaves differently depending on the shape of the land beneath it. Valleys can trap warmth during the day, then release it upward as evening arrives. Moist air rises, cools, and condenses, allowing storms to form suddenly and dissolve just as quickly. Rain may fall on one side of a ridge while sunlight remains on the other. Thunder rolls back and forth between slopes, echoing with precision. Those who live in these regions learn to notice subtle signs. The curve of a cloud, a metallic scent in the air, a moment of unnatural stillness. These small, self-contained weather systems are reminders that not all storms span continents. Some belong only to a single mountain, brief conversations between air and stone that begin and end, unnoticed by the wider world. Entire cities rely on mountain snow for survival each winter. Snow accumulates across high slopes, forming a vast natural reservoir when warmer seasons arrive. This frozen store releases water slowly, feeding rivers that supply homes, farms, and power stations far below. Cities in California depend on snow from the Sierra Nevada across South Asia. Millions rely on meltwater from the Himalayas. This system depends on balance. Too little snow brings drought. Too much melting at once causes floods. Scientists measure snowpack carefully, knowing that small changes in temperature can affect countless lives. Every snowflake that settles in winter is a promise written quietly across the peaks. When spring arrives, the promise flows outward, transforming ice into rivers. To understand mountains is to recognize this generosity, given patiently dropped like frozen drought. As mountains lose snow, rivers downstream can fade away. Rising global temperatures are causing glaciers and snowfields to retreat faster than they can recover. These frozen reserves once released water steadily through warm months, sustaining rivers long after rainfall ended. Now, in parts of the Andes and Himalayas, streams are drying earlier each year. Communities that have depended on meltwater for generations are beginning to feel the change. Rivers that flowed reliably for centuries shrink into narrow channels by midsummer. The impact reaches beyond human life, altering woodlands, forests, and agriculture across entire regions. The loss of mountain snow happens quietly, yet its consequences are vast. The reservoir at the roof of the world is disappearing, and once gone, it will take thousands of years to return. The mountains remember water even as the valleys below begin to forget. So mountain valleys act as natural amplifiers for sound. In certain high basins, echoes behave like reflections in a mirror. Rock walls and curved terrain catch sound waves and send them back again and again. Shout, a cracking ice fall, where distant thunder can rebound across the valley, repeating long after the original sound has ended. Some echoes stretch on, haunting and disembodied, while others distort distance, making faraway sounds feel close. Long ago, people believed these voices came from spirits answering the cliffs. Today, we understand the acoustics behind them. Still, when your own voice returns to you from stone, it rarely feels like simple physics. It feels like dialogue. In rare mountain basins, echoes can linger for minutes. The sound does not vanish quickly, but circles gently, fading in layers, as if the valley itself were listening before finally letting go. A single voice or ringing bell can linger in mountain air for nearly a full minute. In places like the fjords of Norway, volcanic bowls in Iceland, and select Himalayan valleys, sound rebounds between curved rock walls again and again. Each repetition softens and shifts, as if the mountain is reshaping the sound before releasing it. Early travelers wrote of peaks that answered back, carrying words across frozen lakes and amplifying them along stone corridors. Even now, the effect feels uncanny. Sound takes on substance, filling the valley like drifting fog. These long echoes reveal how mountains momentarily store energy, how air and rock work together in resonance. When silence finally returns, it feels deeper than before, as though the land itself has slowly exhaled. Mountains remind us that even a single sound can outlast its source among walls shaped by time. At high altitude, light scatters with unusual brilliance. With fewer particles in the thinner air, sunlight passes through with less diffusion. The sky deepens into a darker blue, and sunrise and sunset stretch into rich bands of gold, crimson, and violet. Ice crystals and fine dust high above can bend light into halos, glories and rare flashes of green at the horizon. At night, Stars appear sharper and more intense, their colors clearer without the softening haze of lower elevations. Shadows grow crisp, distances feel unfamiliar, and the world seems newly polished. Climbers and photographers often describe the light as extraordinary. It is the same sunlight that reaches every place on Earth. Yet here, refined by altitude, it reveals a clarity few ever see. Mountains show light in its purest form. Direct, radiant, and endless, mountains are among the finest places on Earth to view the stars. Far from city glow, where air is dry and thin, the night sky opens fully. From high summits, countless stars emerge, and the Milky Way stretches from horizon to horizon like a pale river of light. Astronomers choose mountain peaks for this reason. The air is steadier, clearer, and less disturbed by moisture. Observatories perched high above sea level can observe the universe with remarkable precision. On lofty summits, telescopes look deep into space through an atmosphere nearly untouched by haze. To stand there at night is to feel suspended between ground and cosmos, wrapped in silence and starlit as the mountains bring the heavens close, as if the universe itself is leaning nearer. Long before modern instruments, people carved high places to study the sky. Ancient cultures recognized that elevation offered clarity. In Mesopotamia, priests ascended step towers modeled after sacred hills to follow the paths of stars. In the Andes, Inca builders aligned stone structures with solstices and celestial events. Greek observers sought clear views from mountain slopes, while ancient Chinese astronomers built platforms on high ground to track comets and eclipses. From these vantage points, early sky watchers traced constellations, marked seasons, and shaped stories from patterns of light. Mountains became both sanctuaries and observatories. Each ascent was an effort to understand the rhythms above. A desire to know the heavens has always drawn humans upward, toward places where the sky feels closer and the view feels timeless. Today, some of the world's most powerful observatories still stand high above the clouds. In Chile's Atacama Desert, the top volcanic peaks in Hawaii, and on remote plateaus in Asia, telescopes operate where air is thin and skies remain clear for most of the year. Scientists and engineers work in silence at these heights. Surrounded by stars on the clearest nights, the Milky Way can cast faint shadows across the ground. These observatories continue an ancient tradition, replacing myth with measurement, yet guided by the same instinct to climb higher in search of understanding. The mountains that once held stories of gods now support instruments that reveal the true scale of the universe, turning ancient wonder into modern discovery. Stone and starlight have always shared the same horizon. Earth's mountains inspire awe, yet across the solar system they would seem almost modest. On Mars rises Olympus, Mons, a vast shield volcano that towers nearly 3 times higher than Mount Everest. Its base spreads so wide it could blanket an entire US. State Mars's weaker gravity and lack of moving tectonic plates allowed this volcano to grow in one place for millions of years, layer upon layer without being pulled apart. Its slopes are gentle and immense, extending hundreds of miles from summit to plain. Other worlds host equally astonishing relief. On the asteroid Vesta, a single peak dominates a body only a few hundred miles across. In the thin Martian atmosphere, Olympus Mons casts a shadow that stretches beyond the visible horizon. These distant mountains remind us that the same forces shaping Earth operate everywhere, patiently sculpting worlds from heat and stone. Some mountains are shaped from metal-rich rock. On Mercury, the innermost planet, the surface bears ridges and cliffs unlike any on Earth. As the planet cooled and contracted, its crust wrinkled and buckled, forming immense scarps that rise more than a mile high and run for hundreds of miles. These features, known as lobate scarps, mark where the surface was compressed as Mercury's interior lost heat. The rock here is dense and rich in metals, reflecting sunlight with a hard, silvery glow. These mountains are records of a planet shrinking over time, their forms frozen into place as internal motion slowed. To stand among them would be to see sunlight glinting all stone that once flowed like molten metal, preserved beneath an unfiltered blazing sky. Far from the sun, ice mountains drift slowly across Pluto. In the cold outer reaches of the solar system, Pluto's surface hosts peaks made of water ice hardened like rock. Beneath them lies a layer of softened nitrogen ice that behaves like a slow-moving fluid. Over long periods, entire mountain blocks migrate, carried by gentle currents of frozen nitrogen below. Some of these icy summits rise as high as major mountain ranges on Earth, glowing faintly in the distant sunlight. When the New Horizons spacecraft passed Pluto, it revealed these wandering peaks sliding across a pale basin known as Sputnik Primitia. They are mountains without deep roots, floating atop an alien surface, proof that motion and change persist even in deep cold and darkness. Venus hides volcanoes larger than any on Earth. Beneath its dense clouds, the planet's surface is dominated by vast lava plains and enormous shield volcanoes. One of the largest, Mount Mons, rises miles above its surroundings and stretches broadly across the land. Much of Venus' surface appears shaped by repeated outpourings of lava. Unlike Earth, Venus shows little evidence of moving plates. Instead, heat builds beneath the crust until it pushes upward, reshaping the surface in sweeping events. Some volcanoes may still be active, releasing heat and gases into the heavy atmosphere. Our observations hint at recent changes, suggesting the planet remains restless. These mountains stand as monuments to ongoing creation, forged in an environment where heat and pressure never truly release their grip. Mars also holds cliffs of staggering scale. Near the planet's equator lies Bell's Mariners, a canyon system so immense it challenges comprehension. It stretches thousands of miles and plunges deeper than Everest is tall. Several times over, rather than being carved by rivers, it formed as the crust fractured and cooled apart near massive volcanic regions. Over time, landslides and ancient floods widen its walls into a maze of chasms and plateaus. From its rim, the view would fade into red haze, the curvature of the planet visible in the distance. Valles Marineris reshapes the idea of mountains entirely, turning the surface into a scar vast enough to dwarf nations. It is a reminder that planets can express their inner forces on scales far beyond ours. Not all mountains belong to planets. Some exist as solitary forms drifting through space, asteroids shaped by ancient collisions. Their surfaces rising into peaks and ridges carved by impact and time. Many asteroids carry mountains of their own. Objects like Bennu and Ryugu rise only a fraction of a mile in height, yet their surfaces are sculpted into ridges and peaks by billions of years of tiny impacts. With gravity so weak, their shapes remain sharp and irregular, like spinning mountains set loose in space. Spacecraft that have approached these bodies found boulders resting on slopes so delicately balanced that a gentle nudge could send them drifting away forever. Some asteroids rotate so quickly that loose material slowly migrates outward, forming faint halos of dust around them. To stand on one would feel like standing on a mountain without a horizon, where direction loses meaning and the stars remain fixed. These wandering peaks remind us that mountains are not bound to planets alone. They exist throughout the cosmos, fragments of creation suspended quietly between light and emptiness. Scientists study mountains to understand how planets change over time. Every mountain holds a record of heat, pressure, and duration. By examining how peaks rise, fracture, and wear away, researchers can infer what happens deep inside a planet. The patterns of uplift and collapse reveal how heat escapes from the core, how crust thickens or thins, and how atmospheres respond to surface change. On Earth, mountain studies reveal the mechanics of plate tectonics. Comparisons with Mars and Venus show what landscapes become when those processes slow or stop. Even the icy ridges on moons like Europa and Enceladus offer clues about how water and rock interact in alien environments. Mountains function as natural laboratories, running experiments in physics and chemistry on scales far beyond human design. Each folded ridge tells a story of balance and transformation shared by worlds across space. Climbing mountains helps scientists understand how life adapts to extremes. High altitudes challenge biology, every level oxygen thins, temperatures plunge, and sunlight becomes harsh and unfiltered, yet life persists. Researchers studying climbers, high-altitude animals, and microscopic organisms living on ice have uncovered remarkable adaptations. Blood chemistry shifts to absorb oxygen more efficiently. Plants alter their internal processes to resist frost. Microbes survive on bare rock near summits, drawing energy from minerals and light alone. Studying these organisms helps scientists imagine how life might endure on distant planets, with thin atmospheres of frozen surfaces. Every mountain ascent becomes an experiment in survival, revealing how creative life can be when pushed to the edge. Mountaineers have often reached places science could not long before satellites and aircraft. Climbers explored the upper reaches of the world. Their journeys led to discoveries impossible from below. New species, rare minerals, and meteorites preserved in ice on Everest. Climbers collected air samples that improved understanding of high-altitude atmospheres. In the Andes and Karakoram, expeditions uncovered fossils that reshaped geological timelines. Even today, climbers contribute vital observations on glacier retreat, unstable rock, and shifting weather. Many mountains remain so remote that only those willing to ascend them can gather data. Each climb blends endurance with inquiry, expanding not only physical horizons but human knowledge itself. Every mountain on Earth is slowly changing shape, though they appear timeless. Peaks are always in motion. Wind smooths their crests, rain deepens their valleys, earthquakes tilt their slopes. Ice presses downward while sunlight causes daily expansion and contraction. Some ranges rise as crust compresses, while others sink as erosion removes weight. Satellite measurements reveal that no mountain is still. The Himalayas continue to rise by fractions of an inch. The Alps lose grains of stone on each year. Volcanoes subtly swell and relax as magma moves below. These changes are too slow to notice, yet they never stop. Mountains are not sculpted once, but endlessly shaped by rhythms of stress and release that stretch across time. Even the oldest ranges continue to change. The warm Appalachians and the ancient mountains of South Africa appear calm, yet deep beneath them, the mantle still flows. Slow buoyant forces lift regions imperceptibly. All erosion quietly lowers than elsewhere. These ancient peaks remind us that no mountain is finished. Each one remains part of Earth's ongoing motion, still rising, still sinking, still becoming. In other regions, the crust cools and tightens, gently drawing mountains down with fierce slow subsidence. Above all of this, wind and water continue their quiet work, sanding peaks into dust and carrying that dust into rivers and oceans. The exchange between uplift and erosion never truly stops. Geologists can trace cycles in which entire ranges rise, disappear, and later reemerge in altered form millions of years afterward. Even a mountain that appears timeless is only one moment in Earth's long breath. The planet is never at rest, and beneath the stillness of ancient hills lies a simple truth. They are alive, changing with each unseen pulse of time. Some mountains vanish almost as quickly as they appear, in areas shaped by volcanoes or rapid tectonic motion. Peaks can rise and collapse within a single human lifetime. Off the coast of Iceland, a volcanic island formed suddenly in the 20th century and immediately began eroding back into the sea. Similar short-lived mountains emerge along ocean ridges or within desert craters, built from loose ash and lava that yield quickly to wind and rain. Some volcanic cones collapse only years after forming, leaving behind circular lakes or shallow valleys. Their brief existence reveals how dynamic Earth's surface truly is. Not all mountains are monuments meant to endure. Some are fleeting expressions of energy flaring briefly before fading away. They remind us that creation and destruction are inseparable, and that even grandeur can be temporary. The true size of a mountain extends far below what we see. Beneath every range lies a vast foundation known as a mountain root, made of dense rock that sinks deep into the crust and upper mantle. These roots balance the visible peaks above, much like the hidden mass of an iceberg beneath the waterline. As erosion lowers a mountain's summit, the crust beneath slowly rises to maintain balance, a process called isostasy. In this way, mountains seem to float upon the planet's interior, adjusting their height as weight shifts. Some roots reach tens of miles downward, forming enormous structures that mirror the mountains above. In reverse, what rises into the sky is only part of the story. The rest lies buried in darkness, pressing gently against Earth's internal heat, unseen yet essential. A mountain's mass can bend the planet beneath it. The sheer weight of a large range pushes the crust downward, curving it like a flexible plate beneath the Himalayas. The lithosphere bends several miles under the load, forming a deep support basin below the peaks. This bending is not permanent. As glaciers melt, rivers remove material, or new rock accumulates, the crust slowly responds, lifting or sinking. As balance shifts, satellites can measure these tiny movements, mapping how Earth flexes under changing weight. The process is slow and invisible, yet constant. A quiet negotiation between gravity and buoyancy that shapes every landscape. Simply by existing, a mountain reshapes the ground beneath it, its influence extending far beyond where stone meets sky. Mountains also create subtle variations in gravity. Because gravity depends on mass, tall and dense ranges exert a slightly stronger pull than surrounding lowlands. Modern satellites can detect these differences with extraordinary precision, sensing changes as small as 1 part in a billion. Missions that map Earth's gravity field reveal how mass moves as glaciers melt, rivers shift sediment, and earthquakes rearrange rock deep underground. The Himalayas, for instance, produce immeasurable gravitational rise, while nearby basins show weaker fields where material has been displaced. These measurements help scientists track water storage, tectonic stress, and even macro movement. Far below the surface, the mountains can gently tug on satellites orbiting hundreds of miles above the Earth is remarkable. Their reach extends beyond land and weather into the invisible force that binds every object to the planet. Some mountain ranges are even used as reference points to calibrate satellite systems. serving as anchors not only of stone, but of measurement itself. Certain satellite systems depend on fixed landmarks to keep their instruments perfectly aligned. Large, stable mountain ranges offer ideal reference points. The Andes, the Rockies, and the Himalayas are mapped with such precision that space agencies use them to verify optical clarity, radar accuracy, and elevation measurements. Because their features change only gradually, these ranges provide reliable standards for tracking sea level rise, shrinking glaciers, and even subtle changes in the atmosphere. Each time a satellite passes overhead, its data is checked against the familiar ridges and valleys below. In this way, mountains have become part of the planet's observing system. Their outlines, once used by travelers navigating by sight, now guide spacecraft circling far above the Earth. The connection between ancient stone and modern technology is quiet but profound. A reminder that landscapes shaped over millions of years still steady our most advanced tools. The science of mountain building has its own name. Orogeny derived from Greek words meaning the birth of mountains. Orogeny describes the forces that fold, lift, and transform Earth's crust into ranges. Scientists who study it explore how continents collide, how rock bends under pressure, and how erosion reshapes what tectonics creates. Each mountain range tells a unique story. Some rise explosively through volcanic activity, others grow slowly as plates press together over vast spans of time. Ancient ranges reveal the long effects of erosion and renewal. By comparing these patterns, geologists reconstruct Earth's surface history, reaching back billions of years. Orogeny links every peak to a larger cycle of formation and decay, showing that mountains are not accidents, but expressions of the planet's ongoing motion. The term captures both the force and the quiet elegance of geology, naming the way Earth lifts itself into form. Mountains appear in every continent, even beneath the oceans, wherever the planet's forces interact. Uplift leaves its mark, from frozen Antarctic ridges to tropical volcanic islands. Peaks rise in response to heat and pressure. Below the sea, immense ranges like the mid-ocean ridges extend for tens of thousands of miles, forming the longest mountain system on Earth. Tiny islands are merely the visible tips of submerged mountains, their bases hidden beneath water and coral. Whether capped with snow or reef, mountains speak a shared geological language. They emerge wherever gravity, heat, and motion find balance. No continent, no ocean floor escapes their influence. The planet's structure is continuous, wrapped in stone from pole to pole. The story of mountains is the story of Earth itself. Each range marks a chapter in the planet's long narrative. Peaks rise through collision, valleys form through collapse, and rocks record the cooling of ancient heat. Together they document the endless movement of crust and mantle. When scientists read this record, they see a world that has never stood still. Mountains grow and wear away, oceans open and close, continents drift, yet the rhythm persists. Every grain of sand once belonged to a summit. Every summit will someday return to dust. Mountains are both memory and forecast, revealing what the planet has been and what it will become. They remind us that permanence is an illusion, and that beauty often arises from change. Within every mountain lies a record of the forces that shaped it. Ridges and stones carry stories, etched in texture, in mineral structure. Some rocks preserve traces of volcanic fire, others hold fossils from long-perished seas. The minerals within them reveal the pressures they endured, and the heat they survived during their journey from depth to daylight. Mountains are memory made solid, the planet's history pressed into stone. To touch one is to reach across immense spans of time. to sense the lingering dance of creation beneath the surface. Every peak, no matter how distant or quiet, carries this memory forward. When we look upon mountains, we are not simply seeing rock. We are witnessing its story, held patiently informed. Mountains do not forget. They stand as silent witnesses to everything that has ever moved, lived, or dreamed upon the surface of our world. Mountains do not forget. Beneath every ridge and meadow, far below snow and stone, the earth continues its quiet labor. Mountains do not hurry. They lift, fold, and settle according to rhythms older than memory itself. Their realm is one of pressure and stillness, where time stretches wide and change arrives, softly, like ash drifting through air. What we see as a mountain is only the surface expression of something far deeper, a visible crest of a process still unfolding in darkness below. As you rest now, imagine those hidden layers moving gently out of sight. Picture continents drifting almost imperceptibly, stone adjusting grain by grain, glaciers tracing patient paths through valleys. Even the most motionless rock carries movement within it. Every pebble along a trail is a fragment of time, shaped from summits that once stood higher than imagination. Mountains remind us that strength lives in endurance, not resistance, and patience, not force. They show us that transformation does not need urgency to matter. What wears away becomes riverbed. What collapses becomes soil. Every ending prepares the ground for something new. Change moves quietly, but it never stops. Let that understanding settle with you now. The ground beneath you is alive, vast and steady. It moves slowly enough for rest, slowly enough to hold you. You are safe within the calm rhythm of deep time. If these quiet journeys bring you peace, you're welcome to like, subscribe, or leave a gentle thought below. It helps others find their way here, one resting mind at a time. For now, there is nothing to do. Just breathe, let your thoughts soften, and allow the mountains to fade gently into sleep.